Good day, I'm Dr. T and welcome to my whiteboard. Today I'd like to talk about the effect of temperature on saturation. Now, wait, what's saturation? Saturation is the idea that you have a solution and you have a solvent and solute or solutes, but you can only go so high on your concentration. At low concentrations, you could add more solute. Yay, more solute. But at a certain point, if you try and add more solute, instead of adding more solute, it just sinks to the bottom. It can't dissolve. The solvent only has so much carrying capacity. Now, of course, this depends on the solute, the solvent, but it also depends on the temperature. Now, if I take a graph, I can graph the amount of solute that a solvent can hold. Say in grams per liter, you might see it in grams per 100 milliliters. It just depends on how you want to express this. And so I've got a couple of different ones, and on the other axis I have temperature. Now for some compounds, a lot of your solids, and also some to do with the liquids, as you go up in temperature, the amount that you can dissolve goes up, like the red or the green lines. Now some things are more affected by this than others. So you will see relatively flat lines and relatively steep lines. But there are some compounds which have actually an inverse relationship. The higher your temperature, the lower the concentration you can get. And this is somewhat counterintuitive, but one class of compounds that does this quite often are your gases. For the most part, gases tend to be less soluble, especially in water, with higher temperatures. Roughly speaking, as the temperature goes up, the particles move faster. If you're in a state where you can move around more, then that's great, especially when it gets hotter. Now, for a solid dissolving into a liquid, that's going to be a more active state. It gives you more possibilities for you to buzz around at. And so the higher the temperature, the more you're going to want to do this. For a gas, however, being in the gas phase, not dissolved, is going to give you more possibilities to buzz around. And so the higher the temperature, the less you're going to want to be dissolved, and the more you're going to want to be in the gas phase. This actually has a couple of interesting applications. Of course, with solids, etc., we know you clean with hot water. Actually, the temperature is not necessarily all that important for some things, but when you are dissolving some compounds, they definitely dissolve quicker if you raise the temperature. Even if you're not reaching saturation, hey, the further away you are from saturated, the faster you tend to dissolve. So, yay, hot water gets it cleaner in some cases for some things. Also with gases, if you notice where the largest fish are, think about it. Where do you think about large fish? Tropics? Not quite. That's where lots of little fish are typically. I mean, they got some big fish, don't get me wrong. A sunfish, that is a big fish. But if you're thinking about, tons of tuna and cod and giant fisheries, that's the northern Atlantic and, of course, the South Pacific. Areas where it's cold. It's easier for fish to breathe when there's more oxygen dissolved in the water, and in those colder climates, near either of the poles, you're going to have more oxygen dissolved in the water, therefore you get more big fish. Yay! Gases have one more player involved. While for solids, if you add more, it just kind of sits on the bottom, gases will be above the solution and they'll be bouncing around. And the more gas you have of that particular type, it doesn't actually matter if it's other types, those don't really affect it. But the more you have of that particular type, what we call a higher partial pressure, which I'll go to in more detail when I jump in and talk about gases. In that case, you're able to get more gas into the solution. There's more gas molecules above the solution, or what we call the headspace, colliding into the solution and going in. With decreased partial pressure, with less gas molecules of that particular type, well, it's less likely that they're going to collide in and more likely they're going to bounce out. This has a couple of real-world applications, especially for your soda. With your soda, you've got your 2-liter bottle of pop, and you don't want it to go flat. I mean, you could just drink it in one sitting. I don't recommend it unless you got some friends to help you, but 2 tricks. 1, we already know that lower temperatures are going to keep gases dissolved, and if you can keep the carbon dioxide dissolved, it won't go flat as fast. So, chill your soda. Second, The more partial pressure of carbon dioxide you have, the greater that is, well, it's not going to go flat, and you already know this. You keep the lid on. So keep your soda as fresh as long as possible. Chill it first, then open it. That'll keep you more CO2 in the container, and try and keep the thing shut as much as possible. With that said, enjoy your beverage and have a wonderful day.